Hello everyone. So in this video I'm going to talk about trees. This is going to be an introduction to trees. So this video is more like just talking about the theories, just introducing some different terms and concepts that we will refer to them regularly. So like root, what is leaf nodes, what are internal nodes, parent, children, sibling, path, height, depth, all of these terms I'm going to just define them in this video. And at the end, I'm going to just give you an example of why we want to have data structures in the form of a tree. So far we have seen linear abstract data types. We have talked about list, different implementation for that. We have talked about queue and a stack, two different restricted form of a list, and all of them were linear structure. It means they will store the data in a in a linear form. It means either you keep it in as an array or a list or a linked list. It is going to be linear connected to each other. You started from one of them and then go to the next one and then go to the next one and then go to the next one. So a linked list or an array doesn't matter. Okay. The linear structures that we have learned are very useful. For example, in implementing any operating system, all the processes are going to be stored in a form of a linked list. If you are going to manage the access to the CPU to different threads or different processes, it is going to be done using a queue. If you are going to run any program, execute the function calls, we need a stack. We have actually seen all of these examples before, right? But linear structures are not enough. Basically, there are a couple of actually issues with linear structures. Some problems cannot be solved using linear structures at all. Next week, in the next lecture, we will learn about a lot of examples. Or at the end of this lecture, I'm going to show you some example that having a tree structure is going to help us a lot. Not only that, the time complexity in a linear structure are kind of slow. So you remember that if we wanted to insert or remove an arbitrary item from a linear structure, from a list, either it is a linked list or an array, if you're going to remove or insert an item, it is going to be in O of n, because you have to actually if you are implementing using an array, you have to shift the items to the left or right. And if you are going to implement it using a linked list, you have to actually iterate over all the nodes to access to that item and then remove it. Okay. But in using the tree structures, we will see that if we have n items, in some cases we can actually get access to some good time complexities like log of n. Remember when we were actually searching for an item in an array, if the items are sorted, we can we can search in the array using a binary search, which works in log of n time. This property is something that we actually are going to implement using trees. So I think I have talked about the why we are going to learn about trees. So from now, I'm going to just give you some definitions, some terms that we use when we are talking about the tree structures. I'm going to define all of them here. So in general, a tree data structure is going to be very similar to the concept of tree from the discrete math, that you have usually we have a root node, and from that root node you have access to some other nodes. I'm actually just make it double, but you have this picture on top that shows a tree. A tree as a data structure basically is going to be an extension of a linked list. In the case of a linked list, each node was having access to one other node. Okay, if you are extending this concept, and instead of having just one link to the next item, if you are making more than one link, it is going to actually create a list, a tree for you. So you can see that I'm just actually extending the same concept of a linked list, but at each node, instead of just accessing to one other node, we can access to more than one node. So in this way, the result is going to be like a tree. That, for example, here from A, I have access to B, I have access to H as well. And from H, I have access to I, access to M. So because each node is going to have access to more than one other node, this is not going to be a linked list anymore. So in a linked list, each node is just connected to one other node. That's why it will be just in a form of a linear structure. When you are allowing each node to have access to more than one other node, it will be a form of a tree. It will be in a form of a hierarchy. Okay, so if I come back to the definitions, let me just erase this here. So one in the trees, remember in the linked list, the first node that is in the linked list, we call it head. So again, when we have actually trees, the first node in the top node is going to be important for us, and we have a different name for that. It is going to be called root. And it is just like, this is the entry to the all nodes. I'm not going to keep, when you had a linked list, you didn't keep a reference to all of these nodes, right? You just keep a reference to head, and from head, you could access to all of the nodes by just traversing over all the nodes. And in a tree as well, I'm just going to keep one reference to the root, and from the root you can access to all other nodes in the in your tree. So the very first, the top node in our tree is going to be called root. So for each node, you can access to 0 or more children. So for example, here H has access to one node, I has access to 3 other nodes, J, K, and L. So we call all those nodes that you have access to them from this node the children of the node. So for I, we have 3 children, J, K, and L. And the node that, the only node that have access to this node is going to be the parent of the node. So here I is going to, the parent of I is going to be H. And be careful, when you have a tree, for each node, there is only one parent, a single parent. This is not a graph, okay? No other node, if I actually go back to this picture, you can see that for all of these nodes, there is only one node directly on top of it and have access to that. For example, F, only E has access to F. Only E has access to G. No other actually node have access to G for G, or for all of these nodes. For example, for C, only B have direct access to that. For M, only H has direct access to that. So here we also have this definition of degree. In when we are actually talking in the context of computer science, the degree of a node in a tree is going to be the number of children for that node. So For I, the degree of this node is going to be 3, right? It has 3 children. It has access to 3 other nodes. And based on that, we can also define this concept of sibling. All those nodes that have the same parent are going to be siblings. So here J, K, and L are siblings of each other because they all share the same parent. Okay, so based on the definition of degree that we have, now we can define the leaf nodes. In a tree structure, all those nodes that have degree 0 are going to be called the leaf node. It means that they don't have access to anything else. As you can see, I have marked all of these leaf nodes in the tree in green. M is leaf node, L, K, all of them. They don't have access to any other node. It's just like the list of children for them is null. So every other node for the tree is going to be called internal nodes. So all of those internal nodes are the white one here. In this picture, you can see that I have marked the leaf nodes as red, and all the internal nodes have been marked with blue. So another concept about trees is unordered trees and ordered trees. If we don't care about the order of the children, we say that the tree is unordered. So it means that, for example, for A, I don't care that the left, for example, child is B and the right child is E, or the left child is E and the right child is B. If you don't care about the order of the children, so you call it unordered tree. But if we care about the order of the children, we call it ordered tree. So in that case, if the tree is ordered, this tree will be completely different than this tree. Okay, and usually in this course, when we are talking about trees, the trees are going to be ordered. So if you have a binary tree like this one, it is going to be completely different than this one. But in some cases, there are some cases that we don't care about the order of the children. For example, if we are storing, in an operating system, the file system is a form of a tree, a hierarchy, right? And we don't care about the order of the folders. All of the folders have been stored, and it is a tree structure, but we don't care about the orders. But in this course, just keep in mind that in this course, when we are talking about trees, usually we just talk about the ordered trees, except the cases that we explicitly explain that we don't care about the orders, and the tree is going to be unordered. The next term that I wanted to introduce here is called path. Path is going to be a sequence of nodes, like for example A0, A1 to AN, where for each node in your path, for example, if you have a path like B, E, G, for each node is going to be the child of previous node. Okay, so from here, B is the parent of E, E is the parent of G. Basically, it is just telling me that if you wanted to access to some nodes, if there is going to be a path in the tree, path should start from some node on the higher levels and go down. So from B, you can access to E, and from E, you can actually reach to G. You cannot go back, for example, from G, you cannot go back to E, or from G, you cannot go to other nodes in the tree which they are not, in the lower level from G. Okay, and we also define the length for the path, which is going to be the number of edges that we need to pass. So if I have a path like this one from B to E to G, the length is going to be 2. You are going to pass this edge, and then you are going to pass this edge. The length of the path is going to be 2. Here it is showing you some example. Here is a path. Let me actually use a different color. Here is a path of length 4. As you can see, it will be started from some node in the upper level, and it is going to end up here. And this is another path here. For example, you started from here and you end up here. The length of this path is going to be 10. As you can see, it's just passing 11 nodes, so it will pass 10 edges. The next term that we are going to use a lot, it is called the depth. We define depth for each node in the tree as the distance from the root. So you can see that from the root, there is a path to all of the nodes in the tree. From the root A, there is a path to H, there is a path to I, there is a path to J, there is a path to K, and this path is going to be unique because the structure is a form of this is a tree, it is not a graph. So the available path that you have is going to be unique, and the distance to each node from the root is going to be called the depth of that node. So in this way, the depth of H is going to be 1, right? This path that you have from the root is going to have length 1. And the distance of M from A is going to be 2. The distance of I to the root is going to be 2. E is going to be at distance 2, at depth 2. C is going to be at distance or depth 2. So when you are defining a depth, basically it's just like you are putting all the nodes, you are in some levels. All these nodes are going to be at depth 1. All these nodes are going to be at depth 2. All these nodes are going to be at depth 3. And so based on this definition, we also define the depth for the root node as well. The path, the distance from the root to itself is going to be 0, right? So the depth of the root is going to be 0. Here we can see another example that the root is here. So the depth of the root to itself is going to be 0. The depth of the root is going to be 0. The depth of these nodes are going to be 1. The depth of these nodes are going to be 2. The depth of all these nodes are going to be 3. Here 4, and so on. Here all these nodes, for example, will be at depth 9. All of these nodes which are marked here at depth 14, and so on. The next term, which is closely related to depth, but it's just like you define it on the other way, is height. We define height for each node as the distance, the longest distance from that node to a leaf node. Okay, so you can see that for all of these nodes, for example, for E, I have actually access to 2 leaf nodes. The distance for both of them is going to be 1, so the longest is going to be 1. The height of E is going to be 1. Let me actually show you another example. For H, you have access to a leaf node in this way, and you have access to 3 other leaf nodes, which are here. Okay, so the distance of H to this leaf node is 1, but the distance of H to these 3 leaf nodes that you actually see here is going to be 2, right? So at the end, we would say that the height of H is going to be 2. So the height is going to be the length of the longest path from V to a leaf node. So if you have access to more than 1 leaf node, you should check all of them, and the longest path is going to be the height of your node. So in this way, we can define the height of all leaf nodes to be 0. The distance, for example, for this leaf node to a leaf node is going to be 0, right? the height of all the leaf node is going to be 0. So based on that, the height of C is going to be 1, the height of E is 1, the height of I is 1, the height of H is 2, the height of B is 2, and the height of the root node is going to be 3, right? If you actually look at it, it's going to be, it's a kind of a recursive definition. For each node, if you know the height of its children, the height of that node is going to be the maximum of between its two children plus 1, right? It's a very nice recursive definition of the height. And so we also define the height for the tree. So if you have a tree, the height of the root node will be considered as the height of the whole tree. This is just by definition. So if you have a tree that only has one node, the root node, it is the only node that you have in the tree, the height of such a tree is going to be 0, right? Because you only have one node, and that node is a root node, and it is also a leaf node. So the height for that is going to be 3. So we usually actually just show it as H. So the height of this tree is going to be 0. You know, in actual world, it's not possible to have a tree that doesn't have any node, which is empty. But in computer science, in the context of computer science, it is possible to create a data structure which is a form of a tree, but you don't have any node in that, right? It's very similar to when you are creating a linked list and head is referring to null. You create a linked list which is empty. There is nothing in that linked list, right? You create an empty linked list. So I can create an empty node as well. An empty tree as well. So the root in that case will be referring to null. So I am going to define this concept, or I'm going to extend the concept of height for an empty tree as well. So for an empty tree, the height, we will define it as -1. This is just, we define it in a form of, this is a convention, and it's going to help us when we are writing the code next week. When I'm talking about the binary trees, you will see that it helps a lot to make coding easier for us. But just keep that in mind, that for empty trees, we define the height to be -1. So here you can see an example that for this big tree, from the root node, you can actually access to this leaf node, or you can access to these leaf nodes here. So basically, the height of the root node is going to be 17. The longest path, which is going to be this one, the longest path to a leaf node, right? So the height of the root is going to be 17, and the height of tree is going to be 17 as well. So this example, I think, is going to give you a good actually intuition about the tree. If the height of the tree is growing, it means that actually the tree is growing from down, and it is going to be bigger and bigger and bigger. Okay, so now we can define two other terms, ancestor and descendant. In a tree, if there is a path from a node to another node, remember that if there is a path from node A to node B, it means that A in the tree is going to be higher in terms of actually levels. So if there is going to be a path from this node to this node, it means that this node A is going to be higher in terms of its hierarchy than this node. So in this way, all those nodes that have access to B are going to be the ancestors of B. So this is going to be the ancestor of B, this is an ancestor of B, this is an ancestor of B. Basically, all those nodes starting from the root until you reach to that node are going to be the ancestor of the node. And if there is a path from A to B, all the nodes along the way are going to be the descendant of A. So this is going to be the descendant of A, this is going to be a descendant of A, this is going to be a descendant of A. So here it's actually showing you that the descendants of B, all of them have been marked in blue. And for example, the ancestor of I, all of them have been marked in red. So based on this definition, you can see that I gave the definition based on this fact that if there is a path from node A to B, we call A the ancestor of B, and we call B a descendant of A. And because from each node, you have access to that node itself, right? So I is an ancestor of itself as well. It is just by definition. I mean, this is just a definition that I gave you from your, this is from your textbook, and maybe in other textbook they would exclude the node itself as the ancestor of that node or the descendant of that node, but it is just by definition, so it's not a big deal. Here is some example that, for example, for this node, all of the descendants have been marked here. I mean, the node itself is going to be this descendant of the node as well. And all of its ancestors have been marked in red. You can see that this is an ancestor of the node, this one, all of them. All those nodes that you will actually visit them if you start from the root until you reach to that node. So I'm done with actually explaining these terms, different terms that we need. Make sure that you get familiar with the terms because we are going to use them a lot. At this point, I'm going to just give you an example of, a simple example that shows you why we care about tree structures and why if we have a data structure in a form of a tree, it makes solving many problems much easier. This example is about XHTML and CSS files for them. So remember, if you have a markup language like the XHTML and you have a document written in XHTML, we sometimes actually prepare some CSS files which basically just explain what is going to be the presentation of the file. So for example, if I'm going to give you an example here, this is going to be a very simple XHTML, and in the CSS files we will give all the formats. For example, I wanted to have the title to be at a specific color. I want to change all the headers to have this specific font. I want all those specific headers H2 to be at a specific color, or I want to use a specific font for the headers. This kind of properties to representing, to showing the page is given using the CSS files. Okay, so for this XHTML file that we have, let me actually show you. You have some title, you have some heading, for example H1. Some part of it has been marked as underlined, right? You have some paragraph tag here. Again, inside the paragraph, some part of it has been marked as underlined. It is a very simple XHTML file. So when we are basically reading an XHTML file in all of the browsers, we will parse it. How we parse it? We use a stack to parse your XHTML file. We have actually talked about this example when we talked about the stacks. And the result, we are going to show the result in a form of a tree structure. Okay, so the author tag that we have, which is going to be HTML, is going to be the root of this tree. It's just like all of the other tags that you have are going to be inside the tree. In this hierarchy, all of them are going to be under the tag HTML. So under the tag HTML, I directly have two other tags. One is head and the other one is body. As you can see, I have two children for HTML tag in my tree structure, head and body. And inside the head, you have another tag, title, right? So for head, there is one child that you call it title. And inside the title, whatever is the text is going to be actually the value of that node. Or for example, here for inside the body, you have one tag h1 and one tag p, which are the direct tags on their body, right? So I would have two children for body. One of them is h1, the other one is p. And again, inside p, you have some text and some other tag. So inside h, I have some direct text, and I also have another node. It's just like I have another child, which is marked as the underline tag. Okay, and inside the underline tag, you directly have some text. Or for example, for the paragraph, the same. You have one tag E and some texts, right? Some text here and some text here. So for P, I would have three children. The first part of the text, the underline tag that I have, and the last children is going to be text. So I'm representing the XHTML file as a form of a tree. So basically, why it makes it easier if I'm parsing it and store it in a form of a tree, because later on when you are, for example, writing some rules in your CSS file to apply over, for example, apply a specific font, apply a specific format, just make it bold, or apply a specific color or whatever. Over this, it's going to be much easier if you work it as a tree. What you are going to do, for example, you are going to show the header. So basically, whatever you have here is going to be, whatever you have here is going to be, let me clean here. Okay, whatever you have here is going to be h1, and whatever is the format for h1, you just directly apply that format for h1. So let's just look at some example of CSS rule that we write. For example, I wanted to change the color of all headers h1 to blue. Okay, so if you are looking at the text directly, it's going to be very complicated to find all of the headers and just apply the color over that. But if you have stored it as a tree, it's going to be much easier. You started from the root node and find all the nodes which are marked as h1. There is only one node, and you directly just apply the color of blue over all the children, all the descendant of h1. So let me show you some more complicated rules. Now assume that I have these two rules, that h1, the header, I want it to be blue, and I also wanted to change the underline text to red. Okay, so in that case, wherever the underline happened, it doesn't matter, you just need to find all those nodes which are marked as underline and just apply the color over that node and all of the descendant of that. So that rule, that format, that a specific format that you want, you will apply it, and as you can see, the color of this one and this one, both of them has been changed to red. So now let's look at some more complicated rules. For example, I wanted to just, I don't want to, for example, change the color of inside the header one from blue to anything else. I want to make sure that always the headers are going to be blue, even if there is an underline in that. Okay, so basically I'm going to write down some new rule. I'm actually updating the rule to be in this form. That only, what this rule means, this rule is telling you that only change the color of underline tag if it is inside a paragraph tag. Okay, so now let's actually look at how we are applying this rule. This is going to be very nice. The thing is, if you have a rule like this, it's just like you are forcing some constraint that the underline should be in a paragraph. So basically, you first find all the paragraph tags. So if you can't find the paragraph tag anywhere else, you just stop. For example, here, there is no paragraph tag in this part, right? You first find the paragraph tag, and then under that paragraph that is starting from the paragraph tag, you look for the underlines. And whenever you see an underline, you apply the rule that change the color to red. So in this way, you are not going to change the color of this node anymore, and the header is going to be in color blue. It's not going to change that. Only this part of the text is going to be changed. So now think about it. If you were working on the a raw XHTML document, which is just text, if you are going to apply such a rule, whenever you find any underline, you have to actually just be careful that there is no other paragraph tag before that. It's going to be much harder if you are just reading the text in a linear order, starting from the top and going to down, and you wanted to apply all these rules. When you are representing it in a form of a tree, it's clearly much easier. You started from the root, you find all the paragraph nodes, and after you find each paragraph node, then you look for the underline nodes and, for example, apply this specific rule. So that's all I wanted to actually discuss in introduction to trees. This is going to be corresponding to chapter 18 of your textbook, and if you have access to this, the book, The Art of Computer Programming, chapter 1 of Donald Knott, this is going to actually cover that one as well. But you can actually just read the textbook chapter.